class. In continuation of the lectures regarding electrochemistry and galvanic cell, we will study the thermodynamics of a redox reaction. We have seen that in a galvanic cell, we convert chemical energy into electrical energy to do some sort of electrical work. For example, running an electric motor or lighting an electric bulb. So electrical energy can be calculated by some other formula which is given here, and this is given as charge multiplied by voltage, which can be also equal to the work done by the system, electrical work done by the system. The charge is coulombs. The charge is represented by coulombs, and the cell voltage is given by cell potential is given by volts, and its unit will be joules, which is the unit for energy or work. Now we have to calculate the total amount of charge that will be transferring in a certain chemical reaction, and that can be calculated from the number of electrons and charge on 1 mole of electron. We need 1 mole because we rather want to standardize the charge units. So what we can do, we can calculate the charge on 1 mole of electron. Charge on 1 mole of electron is given by charge on 1 electron multiplied by the Avogadro's number, which is given here. 1.602 into 10 to the minus 19 coulombs is charge on 1 electron, and multiplied by 6.02 into 10 to the 23, this is the Avogadro's number of electrons. So multiplying these two will give the charge on 1 mole of electron. It is a constant quantity known as Faraday's constant after the name of the scientist who calculated first of all this charge on 1 mole of electron. Charge on 1 mole of electrons. So the total charge will be the number of electrons multiplied by the charge on 1 mole of electrons, given here. NF. N is the number of electrons, F is the Faraday's constant, charge on 1 mole of electrons, and where N is the number of moles of electrons exchanged between oxidizing agent and reducing agent in an electrochemical process. And we can calculate the electrical energy, which is equal to the maximum work done or the electrical work done given as charge, which is NF multiplied by voltage, which is E cell, that is minus NFE. This is the maximum amount of work done in an electrochemical process. We use the negative sign here because the work is being done by the system on the surroundings. And in thermodynamics parameters, we have introduced another quantity, delta G, which is the change in free energy. Actually, this change in free energy tells us about the direction of the certain reaction. If the value of delta G is negative, then the reaction is spontaneous in a certain direction. Spontaneous means it can happen on its own. If delta G is positive, it means the reaction is non-spontaneous in that direction. And if delta G is equal to 0, then it means that the reaction is at equilibrium. It means it is reversible. But anyways, we will give here the maximum work done in terms of change in free energy, which is equal to delta G is equal to minus NF E cell. If the reactants or products are in their standard state, that is at 1 molar concentration or 1 atmospheric pressure, or the temperature is 25 degrees centigrade, then we can use the standard free energy, change in free energy for standard conditions, which is given as delta G naught is equal to minus NF E naught cell. In this case, we will use E naught cell, standard potential, for standard change in free energy. So standard change in free energy is also related to equilibrium constant in this equation. Delta G naught is equal to minus RT natural log of K. K stands for equilibrium constant. And we also know that delta G naught is equal to minus NF E naught. Equating both of these equations, we can end up with E naught cell is equal to RT over NF into natural log of K. These negative signs will cancel out, and E naught cell can be uh, calculated by using this equation, provided if we know the equilibrium constant. Now, if the temperature is also standard, that is 298 Kelvin, we can put this in this equation. R is gas constant, temperature is 25 degrees centigrade, that is 298 Kelvin, and we can keep it as it is changeable, and F is Faraday's constant, which is 96500 joules per voltage and mole. This is Faraday's constant, charge on 1 mole of electrons, and we can get 0.0257 divided by n into natural log of k. This is the V is actually the after cancellation of these units, V uh, V stands here. And if we convert this natural log into log 10, which is natural log is equal to 2.303 log of 10 base 10, and if you multiply it with 2.303, we can get another equation in log, which will totally this equation for E naught cell is equal to 0.0592 divided by n into log of k. So what we can see that how potential, yeah, standard potential is related with equilibrium constant. Here we can see that E cell is related with change in free energy, and here E cell is related with equilibrium constant. So if we know E cell, we can find the change in free energy. If we know equilibrium constant, we can find the potential, or if we know the potential, we can find the equilibrium constant, vice versa. Provided one is known, one is unknown and other parameters are known, we can find the unknown. Okay, now what about the situation when we have no standard conditions? The concentration is not 1 molar, temperature is not 25 degrees centigrade, or the pressure is not 1 atmosphere. Then how we can calculate the E cell? So we can calculate E cell by using Nernst equation. Nernst equation is used to calculate the E cell when there are no standard conditions, or concentration is not 1 molar, and the temperature and pressure are also different. So consider a redox reaction given here, that is A moles of A are reacting with B moles of B to give C moles of C and D moles of D. Small a letters A, B, C and D are the number of moles of stoichiometric coefficients participating in the reaction. Now for this reaction, there is a thermodynamic relation given as delta G is equal to delta G naught plus RT natural log of Q. Now this is the thermodynamic relation, and it relates the change in free energy with the standard change in free energy. You can see that delta G is equal to delta G naught plus RT natural log of Q. And what is Q? Q is the reaction quotient. This is the ratio of products to reactants. You can see here the formula of Q is equal to that we multiply C and D, which are concentration of C and D, which are the products, divided by concentrations of A and B, which are reactants. So ratio of products to reactants, this is known as reaction quotient, and depends upon the activities or concentrations of different reactants and products involved in this chemical reaction. We also know that delta G is equal to minus NFE. We have derived previously, and then based on standard conditions, delta G naught is equal to minus NF E naught. Now we can use these values for delta G and delta G naught and plug them in this equation, and we end up with the relation for E cell, which is given as E is equal to E naught minus RT divided by NF into natural log of Q. You can just put these values and play around and get this equation. This is known as Nernst equation. What is it is doing? It is relating the E cell, which is the potential at non-standard conditions, to E naught, which is the potential at standard conditions. So it is relating the E with E naught through this factor. E is equal to E naught minus RT over NF natural log of Q, where Q is the reaction quotient. Now if the reaction is happening at 298 Kelvin, and we can plug in the values of R, temperature 298, and we keep it as it is, and F, the charge on 1 mole of electrons, which is 96500 coulomb. So we can get this, we can simplify it into this relation: E is equal to E naught minus 0.0257 divided by N to natural log of Q. And if we further convert it into log of base 10, then we can get this value: E is equal to E naught minus 0.0592 divided by N to log of Q. So this is Nernst equation at 25 degrees centigrade. Now consider this classical example of zinc and copper electrochemical cell, Daniell cell. The zinc plus copper 2 plus is giving zinc 2 plus plus copper solid. Now here 2 electrons are transferred from zinc to copper. So we can use the Nernst equation to derive E cell. And we can put the value of E is equal to E naught, which is 1.10 volt for this Daniell cell for zinc copper combination, minus 0.0257 divided by 2, provided the temperature is 298 Kelvin. Here we have also assumed that temperature is 298 Kelvin. Otherwise, we will use this equation, E naught minus RT. We have to use the other value of T if the temperature is different than 298. But in this case, the temperature is 298, so it is simplified to 257 divided by 2. 2 is N, which is the number of electrons which is actually transferring from zinc to copper. Then natural log of, now we have put here Q. For Q, in the numerator we put the products, which is products are zinc 2 plus and copper solid. And but you see here that we have not written copper solid. Why? Because the concentration of pure solids or pure liquids are ignored. We do not put them in this expression for Q. Wherever you find any solid or pure liquid, you just remove it, you ignore it, you don't write it. So we will just write zinc 2 plus, which is the product, divided by, then we put the reactants in denominator, and in reactants we will ignore zinc solid, we'll just consider copper 2 plus aqueous. So this is the Nernst equation for zinc copper Daniell cell. Now what you have seen, that if this ratio, that zinc, this is for Q, zinc 2 plus divided by copper 2 plus is less than 1. If it comes out to be less than 1, that is in the points, and then its natural log will be negative. It will be a negative number, and this negative will cancel out with this negative and will become positive, and E will become, overall the E will become positive, right? This is one case. Or in other case, if this ratio is greater than 1, if zinc over copper, zinc 2 plus over copper 2 plus ratio is greater than 1, then this natural log will be a positive number. And if this natural log is a positive number, then this positive will be with this minus will become negative, and then it will depend that if this negative is less than E naught or greater than E naught. So then this E can be either positive or negative if this value is negative. So what does it show? If E is positive, if total overall E becomes positive, then it means the reaction is spontaneous, it can happen on its own. Or if E is negative, If this difference comes out to be negative, then overall this E cell will be negative. Then what does E negative means? That the reaction cannot happen on its own, or you have to provide energy to let it happen. So this is a Nernst equation, and it relates the standard EMF with non-standard EMF. Now, the first numerical is calculate the equilibrium constant for the following reaction at 25 degrees centigrade. 1 mole of stannous solid is reacting with 2 moles of copper 2 plus, and it is giving the stannous 2 plus. 1 mole of stannous 2 plus 2 moles of copper plus 1. Now class, you have to be very careful in looking at the oxidation states of the reactants and products. You can see that in the reactant the copper is 2 plus, but in the products the copper is plus 1. Single plus mean it is plus 1. So now the reaction is not completely to copper solid, but the reaction is towards formation of copper plus 1. Now, when you solve the numerical, you have to identify the separate anode and cathode half cell reactions. You have to write them down. At anode, oxidation is taking place. So what is happening? Stannous solid is oxidizing to stannous 2 plus along with removal of 2 electrons. And then at cathode, reduction is taking place, and here the reduction is a bit different. How it is different? That 2 moles of copper 2 plus are accepting 2 moles of electrons to give 2 moles of copper plus 1. It means that now this time individual copper 2 plus is being reduced by 1 electron to give copper plus 1. To balance the reaction, we are using 2 moles of copper 2 plus. Why? Because 1 mole of stannous is giving 2 moles of electrons, and this 2 moles of electrons will be picked up by 2 moles of copper 2 plus. So that's how this redox reaction is completed. Now we have to calculate the equilibrium constant, so we need to know the E cell. We have to look at the relation or find a derivation which relates E naught cell with equilibrium constant, which is given here. E naught cell is equal to 0.0257 divided by n to natural log of k. Since the reaction is taking place at 25 degrees centigrade, so we are using this simplified version. Otherwise, you can use, let me check the other relation, this one. If the temperature is different, then you can use this relation. E naught cell is equal to RT over NF into natural log of K to find out this equilibrium constant. Okay, coming back to numerical, we can put the values of E naught cell. We will rearrange it. Natural log of K is equal to E naught cell multiplied by n. We are taking n on this side, so it will be multiplied. It was being divided here, and then 0.0257 will be divided here. Okay, but before that we need to know the E naught. So E naught cell can be calculated by this formula: E naught cathode minus E naught anode. These values you can get from electrochemical series. For copper 2 plus, copper plus 1 reduction potential, and for stannous 2 plus 2 stannous reduction potential. You will take these values from electrochemical series and you can calculate the E naught cell, which comes out to be 0.29 volts. Now putting this value of 0.29 volts, and we know that n is 2, we can calculate the equilibrium constant K. Here you have to play a little bit, because to find out K you have to take inverse of log, inverse of natural log, that will be exponential form. If you will take inverse of these this side, then you can calculate K. It comes out to be 7 into 10 to the 9. You see this huge value of K. What does it tell? It tells that equilibrium constant is high. It means the reaction is favorable in forward direction. This reaction is favorable in forward direction because it has high value of this equilibrium constant. Okay, let's have a look at another numerical. Calculate the standard free energy change for the following reaction at 25 degrees centigrade. Here 2 moles of gold are reacting with 3 moles of calcium 2 plus. Concentrations are 1 molar, and they're giving 2 moles of gold 3 plus. Concentration is 1 molar plus 3 moles of calcium. You have to look up for the formula that relates standard free energy with E. And this is the formula: delta G naught is equal to minus NF E naught. To find delta G naught, you need to know N, F, and E naught. N, you will first write the anode and cathode half cell reactions. From there, you will figure out what is N. F is Faraday's constant, and E naught we can calculate from this formula. E naught cell is equal to E naught cathode minus E naught anode. So let's first write the anode and cathode half cell reactions. That at anode, oxidation is taking place, that is gold is oxidizing to gold 3 plus. If you write it with the balanced number of moles which we can take from this above equations, then 2 moles of gold are giving 2 moles of gold 3 plus. It means one individual gold is giving how many electrons? 3 electrons. Individual gold atom solid will give 3 electrons, but 2 moles of gold will give 6 electrons. It means that if you write the without this balancing, that is without this 2, here 3 will come. 1 gold will give 3. So multiply by this whole equation by 2. Why we have to multiply it by 2? Because in this overall main reaction, for balancing we write 2. So after multiplying, we get how many electrons? 6 electrons. That is 2 multiplied by 3. Now for the cathode reduction reactions, what does it give? That 3 moles of calcium 2 plus are reduced to 3 moles of calcium solid. It means there are 3 moles of calcium 2 plus are reduced by 6 electrons, which will give 3 calcium. It means individual calcium is being reduced by how many electrons? 2 electrons. Each individual calcium 2 plus is being reduced by 2 electrons. If you remove this 3, so if for individual reaction, calcium 2 plus plus 2 electrons will give 1 calcium solid, and if you multiply it by 3, then it will be balanced, and you will multiply this 2 with 3 and it will come out to be 6 electrons. So overall 6 electrons are being removed from 2 moles of gold, and these 6 electrons are being added to 3 moles of calcium. So you have to be very careful when you are splitting it up into individual anode and cathode half cell reactions. Here the balanced chemical equation is given, and if it is not balanced, you have to balance it first, and then you have to split it up into anode and cathode half cell reactions and see how many number of electrons are being exchanged. The total number of electrons have to be equal, which are being removed and then accepted. They have to be equal. It doesn't matter if you have different number of moles at anode and different number of moles of species at cathode. It doesn't matter. What as long as the total number of electrons being removed and being added are same. So we write the formula for E naught cell is equal to E naught cathode minus E naught anode, and taking these values from electrochemical series, we can calculate the E naught cell, which is minus 4.37 volt. Now putting this value of E naught cell into this formula, delta G naught can be calculated as given here. We have calculated N, which is 6, right? And then F is Faraday's constant 96500 and coulombs, and then we multiply it with this E naught cell, which is minus 4.37, and the value comes out to be 2.53 into 10 to the 3. The value for delta G naught is positive. This negative is cancelled by this negative from this E naught cell. So this large high value of delta G naught tells us that the reaction is uh, not favorable in the forward direction. This is positive value, and it is counterchecked by the negative sign for E naught cell. The reaction is not favorable or is not spontaneous. It cannot happen on its own in the forward direction. Forward direction means that gold and calcium 2 plus will not react to give gold 3 plus and calcium. Or it means that the reaction favors the reactants. The reactants will be sitting as it is. They will not change into products. Okay, coming to the last numerical, predict whether the following reaction would proceed spontaneously at 298 Kelvin. The reaction is given here, and the concentrations of reactants and products are also given, which are different, which are not 1 molar. It means this reaction is taking place under non-standard conditions because concentrations are not 1 molar. So what we will do, we will use Nast equation to predict whether the reaction is taking place or not. What we will see, we will see the sign. We will calculate E from Nast equation, and we will look whether it is negative or positive. Okay, to calculate E, we have to use this formula. E is equal to E naught minus 0.0257 over N. We have used again this formula because the temperature is 298. Otherwise, we can use the other formula, which is E is equal to E naught minus RT over NF natural log of Q. If temperature is not 298, then we can use this formula. Since temperature is 298, so we are using this formula in the numerical. Okay, now before going to Nernst equation or even calculating E naught cell, we will see the individual anode and cathode half cell reactions. For cobalt, it is simply oxidizing to cobalt 2 plus with removal of 2 electrons, and for iron 2 plus, it is picking up these 2 electrons to give iron solid. It's quite simple since 2 electrons are being exchanged. So N is 2, and E naught cell is calculated by putting the values, by taking the values from electrochemical series, which comes out to be minus 0.16 volt. Okay, now we will put these values in this formula for Nernst equation. N is 2 and natural log of Q. Quotient which is the ratio of products to reactants. In products we have cobalt, we will ignore iron solid, and in reactants we have iron 2 plus, we will ignore cobalt solid. So putting these values, we end up with E is equal to minus 0.14 volt. You can see that the E calculated is negative. It means the reaction is not spontaneous in the this direction given. That cobalt will not naturally react with iron 2 plus to give cobalt 2 plus and iron solid. Since, and this is again counter checked by a value of E naught cell. E naught cell is also negative. Uh, it also what does it mean? It means that whether it is E naught cell or E cell, the sign is negative. For both of these, the sign is negative. So it means the reaction is cannot happen on its own. It is non-spontaneous in this forward direction. And if you want to carry out this reaction, you have to provide externally some energy to carry out this reaction.